So like I said this morning, I brought some slides of the Cayley graph of the integer Heisenberg group. So remember, the Heisenberg group is the group of upper triangular 3x3 matrices with ones along the diagonal. The integer Heisenberg group is that same group, except you require that the coefficients are integers. And the integer Heisenberg group has a presentation like this. There are three generators, x, y, and z. X, the commutator of x and y is z, and x commutes with z, and y commutes with z. And this is the Cayley graph. So the x-axis goes left and right. The y-axis goes into and goes front to back. The z-axis goes up and down. And the edges in the Cayley graph, the vertices in the Cayley graph are the integer points in R3. And the edges in the Cayley graph connect, I've colored them red. You can't really see it, but those edges are colored blue, and the ones going up and down are in black. And if you do the matrix multiplication yourself, you can see that if you multiply by x, the x coordinate increases by 1. If you multiply by y, the y coordinate increases by 1, and the z coordinate goes up or down depending on the x coordinate. And if you multiply by z, the z coordinate goes up by 1. So you have a graph like this. And because this is a Cayley graph, you can see the relations in the presentation of the group inside the Cayley graph. So if I start at any point here and I multiply by x and then z and then x inverse and then z inverse, I get back to where I started. If I start at any point and I multiply by y, z, y inverse, z inverse, I get back to where I started. That corresponds to these two relations. And if I start at any point and I multiply by x, y, x inverse, y inverse, then I end up one above where I started. So this is why I was saying before that you can go from any point to any other point through horizontal curves, because the blue edges and the red edges here are all parallel to those horizontal planes. In fact, the red edges and the blue edges at each point generate that that field of tangent planes V1. And so you can see that all the tangent planes, all of those planes contain the x direction, and then they tilt as the x coordinate increases. And you can go, all the red and blue edges are horizontal curves, so you can go from any point in the lattice to any other point in the lattice by traveling along red and blue edges, right? So you can see a lot of the geometry that we talked about in the real Heisenberg group. You can see it in the Cayley graph of the integer Heisenberg group. So like I said, you have this relation that x, y, x inverse, y inverse is equal to z. But you also have bigger copies of that relation. Remember, we have this automorphism of the Heisenberg group that sends the point x, y, z to tx, ty, t squared z. And this is an automorphism of the Heisenberg group. So if we act on this relation by that automorphism, say we double the x coordinate, double the y coordinate, multiply the z coordinate by 4, we get a bigger copy of that same spiral. Same thing if we scale it even higher, we get a bigger copy of that same spiral. Here we're going 4, x to the 4th, y to the 4th, x inverse to the 4th, y inverse to the 4th, and that moves 16 steps up in the z direction. And so, well, what can you tell from this? Well, the asymptotic cone of the Cayley graph of the Heisenberg group is going to be the space that we get as the limit of taking larger and larger scalings. So in particular, we should be able to understand the asymptotic cone of the Heisenberg group, we should understand the geodesics that connect points that are very far apart. And if I take 2 points that are very far apart, then what this tells us is that the geodesic in the Cayley graph between 2 points that are very far apart is going to use almost entirely red and blue edges. Because, these relations, where we're writing a power of z in terms of x's and y's, the expression in terms of the x's and y's gets more and more efficient as the scale increases. So in our first example of this relation, you can go one step in the z direction by doing 4 steps in the x and y directions, or you can move 4 steps in the z direction by moving 8 steps in the x and y directions, or you can move 16 steps in the z direction by making 16 steps in the x and y directions. And that's getting more and more efficient as the powers increase. In general, you can make n squared steps in the z direction by moving 4n steps in the x and y directions. And so in particular, if you have 2 points that are separated a long distance apart, then the shortest curve between them is going to use mostly red and blue edges. Because if it used a lot of black edges, then you could replace those black edges with some big spiral. Okay? So you can see the scaling automorphisms that we talked about showing up in the Cayley graph, because, well, to go from this picture to this picture, you apply the scaling automorphism, you shrink the z direction by 4, you shrink the x and y directions by a factor of 2. You can see you can see that geodesics in the asymptotic cone of this Cayley graph should, just like geodesics in the asymptotic cone of the real Heisenberg group, should mostly go in the red and blue edges, along the red and blue edges. And if you have geodesics that mostly go on the red and blue edges, or almost entirely go on the red and blue edges, then that means that they're going along this distribution of tangent planes. So at each point, we stick a tangent plane that's spanned by the red and blue edges. Remember, we said that our tangent planes were going to be spanned by the vectors 1, 0, 0, and 0, 1, x. Those are the red and blue edges there. And then in the sub-Riemannian metric, all our curves are going to be tangent to these planes. In fact, here is a picture of a geodesic in the sub-Riemannian metric on the Heisenberg group, and you can see, and we'll talk in a little bit about why this is a geodesic, but you can see how this curve is always tangent to that distribution of tangent planes that's tilting as the x-coordinate increases. Okay? Okay.
Sorry.
Yeah?
Can you go to the report?
Uh-huh.
Yes, so why are the blue edges faster than the one?
Why are the blue edges faster than the black ones?
They just go, I mean, one blue edge is just one red and one.
Well, no. So the embedding of the Heisenberg group in R3 is not a very nice embedding, and you can see that here. I mean, this is the usual embedding of the Heisenberg group in R3, and we have a bunch of edges that all have length 1 in the Cayley graph, but they're separating points that are further and further apart in R3. But this is homogeneous. This picture is homogeneous. If the graph in the neighborhood of, say, this point should be exactly the same as the graph in the neighborhood of this point. So no matter where you start, not just here, if I start here and then I move, let me start here so I can actually reach the points I'm pointing to. If I start here and I move x direction, y direction, back in the x direction, back in the y direction, then I end up one step above where I started, just the same as if I started over there. Does that make sense? Yeah. Okay. Yeah, so it's just an artifact of the embedding that the blue edges look longer than the red edges. Really, there's an automorphism of the group that will take the red edges to the blue edges, that will swap the red and blue edges. So, okay, so let me turn this off. Do I need to push it twice? Okay, there it goes. Again? Okay. Okay, so that's our metric. What can we say about this metric? So I think this morning I said, that ST, this scaling automorphism, so just to write it again, this is dx dy dz squared, t squared z. This preserves the distribution of tangent planes. Remember, our distribution of tangent planes is the kernel of dz minus x dy. It preserves the distribution of tangent planes, and so in particular, if you have a curve that's horizontal, then it's going to then any scaling of that curve is horizontal. So it preserves horizontal curves. And because of that, because our distances are defined in terms of horizontal curves, that means it scales this CC metric. What else can we say? If I have one way of understanding horizontal curves is that every horizontal curve, there is a projection map from the Heisenberg group to R2, to the xy plane. And if gamma is a curve in R2, and let's say is piecewise smooth, and let's say that gamma of 0, say the curve starts at the point 0, 0, then there is a unique lift of gamma. And let's call that lift gamma twiddle, such that gamma twiddle is horizontal. Gamma twiddle starts at the origin, and the projection of gamma twiddle is equal to gamma. Namely, if we write gamma as, if we write the coordinate functions of gamma as, say, gamma sub x, gamma sub y, then gamma twiddle of t is equal to gamma of x of t, gamma sub y of t, and then the integral from 0 to t of, what do I need? Of the x-coordinate times the derivative of the y-coordinate. Let me make that a tau. Basically, what this is, all of our horizontal planes, all our planes in V1 project isomorphically to the plane R2, and this is just the lift. If I have a vector in R2 and I lift it to one of these horizontal planes, the z component of that lift is going to be the x-coordinate of my the x-coordinate in my space times the y-coordinate of the vector. So we integrate those, we get this, and this is the unique lift of a curve in R2. And in particular, if gamma is a closed curve, then the difference between the z-coordinate of the lift at time 1 and the z-coordinate of the lift at time 0 is going to be the integral from 0 to 1 of the x-coordinate times the derivative of the y-coordinate. And this integral is something we've seen before. If gamma is a closed curve, then this integral of gamma is going to be the signed area of gamma. And so in particular, we can use this to tell us about the geodesics in the Heisenberg group. So because of this, that means that if I have a curve, that connects the point 0, 0, 0 to the point 0, 0, 1, if I have a horizontal curve from 0, 0, 0 to 0, 0, 1, then its projection is a curve of signed area 1. If that curve is a geodesic, then that means that its projection is the shortest possible curve which has signed area 1, which means that its projection is a circle. So this implies that the geodesic, in fact, there are multiple geodesics between 0, 0, 0 and 0, 0, 1. The geodesics from 0 to 0, 0 to 0, 0, 1 are the lifts of circles. Through the origin, like the one I had on the slide. That was the lift of a circle through the origin. And so in particular, we can calculate the distance in the CC metric between the origin and the point 0, 0, 1. It's the circumference of a circle it's the circumference of a circle whose area is 1, which means that it is what is it? It's root 2 root pi is 2 root pi. And furthermore, because of the scaling inequality or the scaling automorphism, we know the distance from 0, 0, 0 to 0, 0, z. Because of the scaling inequality, we get a geodesic from 0, 0, 0 to 0, 0, z by rescaling a geodesic from 0, 0, 0 to 0, 0, 1 by a factor of root z. And so it has length 2 root pi root z. Is it okay? Okay. More generally, the approximate distance in the CC metric from 0, 0, 0 to xyz, this is going to be roughly up to a multiplicative constant. This is going to be on the order of norm x plus norm y plus root norm z. The ball of radius r around 0 is a box, is roughly a box. And it's roughly a box with dimensions r by r squared box. And in particular, the volume of that ball measured in R3, the volume of a ball like that measured in R3 is r to the 4th. And so in order to cover the unit ball by balls of radius r, we need roughly r to the 4th balls. And so the Hausdorff dimension of the Heisenberg group with the CC metric is going to be 4. So this is a 4-dimensional. So this is a space that has topological dimension 3. It's homeomorphic to R3, but it has Hausdorff dimension 4, basically because, well, we have this estimate of the distances on the z-axis on vertical lines. Because the distance between 0, 0, 0 and 0, 0, z is on the order of root z, that means that the vertical lines all have Hausdorff dimension 2. And so we've got 2 dimensions worth of vertical lines, each of dimension 2. That gives us a space with Hausdorff dimension to 4. Is it okay so far? Okay. What do I want to say? So that's what the space looks like. So that's what the space looks like. Let's start looking at surfaces in the Heisenberg group. And just like before, just like with the solvable groups, we're going to be looking at surfaces in the group itself, surfaces in H3 with the Riemannian metric, and we're going to be looking at surfaces in the asymptotic cone, surfaces in H3 with the CC metric. So it turns out, and like I said, we're looking for connections between surfaces in the group, surfaces in the Riemannian metric and surfaces in the sub-Riemannian metric. So first, let me just say, the Dane function of the Heisenberg group is on the order of L cubed. And the reason for this, the reason for this has a lot to do with the quadratic distortion of the vertical axis. It has a lot to do with the fact that you can move n squared distance vertically by way of a horizontal curve of length on the order of L. So if I want to, in order to prove this, let me give you an example of a curve of length on the order of L that's difficult to fill. So for that curve, I'm going to let gamma be a curve in R2, namely this curve. So here is the x-axis and the y-axis, and I am going to draw a curve like so. I'm going to go like this, and each of these sides has length L, so my curve has length 8L. And because I went around this, I went counterclockwise around this, and then clockwise around this, the signed area of this curve is 0, and so this lifts to a closed curve. And that closed curve is going to look like this. So we have, here's my x-axis, y-axis, z-axis. I'm going to start at the origin. I'm going to go distance L along the x-axis, distance L along in the y direction. And when I go distance L in the y direction, that's going to be like that. And it's going to move me up by distance L squared, because when you move in the y direction, you also move in the z direction corresponding to the x coordinate. Then I'm going to move back in the x direction. So far we've done 3 segments of the curve, and then back in the y direction. And now, because I'm at the my x coordinate is 0, my z coordinate doesn't change. So I'm still L squared above the xy plane. Right? And then we just continue symmetrically, like so, and like so. So this is my curve. It's a lift of that figure 8 there. And it spends part of its time on the it spends part of its time at z coordinate 0, then it goes up to z coordinate L squared, stays at z coordinate L squared, and then goes back to z coordinate 0. Right? Okay, so why does this have cubic, why is the filling area of this, why is the filling area of this curve cubic? The answer is basically that this curve intersects a cubically large number of horizontal lines in the x direction. So remember, all of my horizontal lines in the x direction are parallel to the x-axis in R3, so they all go like that. And so there are going to be cubically many of those lines that pass through this circle, because this curve has horizontal extent about L. I mean, the x-coordinate and the y-coordinate vary by about L, and the z-coordinate varies between 0 and L squared. And so the number of horizontal lines that pass through this curve is going to be cubic. So we can see this. Another way to say this is by looking at the projection from the Heisenberg group to the YZ plane. I'm just going to project straight along horizontal lines to the YZ plane, if we project along horizontal lines to the YZ plane, then we get a picture like this. So this is going to project, this line here is going to project to a point, and then we go to y coordinate, we go to the point L squared, and then we go across the top of the triangle like so, and then we go down the other side of the triangle. So if we project to the YZ plane, we end up with a triangle like this, which has area L squared, or sorry, area L cubed. And you can check, and this is an important calculation to do, because otherwise this argument doesn't work. You can check that that if you take the Riemannian metric, the left invariant Riemannian metric on the Heisenberg group, then this is an area decreasing map from the Heisenberg group with the Riemannian metric to the YZ plane. And this is an important calculation to make, because it's not true that if I did the same thing in the xz or to the xz plane, if I projected to the xz plane, so that this line would project to this point here. If you project to the xz plane, this is not an area decreasing map. This is not an area decreasing map in the xz direction, because the horizontal planes tilt. Because there are going to be horizontal planes that take up more and more of this, more and more area. But this is an area decreasing map in the if you project to the YZ plane, and if you're careful, you can define a map to the XZ plane that is area decreasing. It's just not the obvious map. Is this okay so far? Sorry? Sorry? Well, yeah, okay, so let me finish. So this is an area decreasing map from H3 to the YZ plane. So in particular, if I have a disk whose boundary is this curve, then its projection has to be this triangle here. The area of this triangle is on the order of L cubed. So that means that the filling area of gamma has to be at least the filling area of this triangle, where we consider this triangle, where we fill this triangle in the YZ plane, and we know what the filling area of this triangle is. This is the boundary of a triangle of area L cubed, and so that tells us that the filling area of gamma is at least L cubed. Is it okay? Oh, the inequality the other way. The inequality the other way is how does this work? So this shows that it's at least that it's greater than or equal to L cubed. In order to show that it's less than or equal to L cubed, you have to show the inequality the other way. The way you prove the inequality the other way, and this is mostly just a calculation, the way you prove the inequality the other way is that if gamma is a curve of length L, and suppose that gamma is based at the identity, then the homotopy h sub t of x is equal to s sub t of gamma of x. Basically, this is the homotopy that takes, here's your curve, here's your curve gamma, and then we just use the scaling map to scale everything down to the identity. Then this is a homotopy that takes gamma to a point, and you can check that the area of this homotopy is on the order of, is at most on the order of L cubed. I'm not going to do that here. This is because it's just a calculation. But that's this is this is the calculation you need to do to actually show the upper bound. Is this okay so far? Okay. So we have that surfaces in the Heisenberg group are surfaces in the Riemannian metric on the Heisenberg group grow cubically with the length of with the size of their boundary. How does this correspond to the how does this match up with what happens in the asymptotic cone? Well, if gamma twiddle is as before, which is to say, if gamma twiddle is the lift of this figure 8 curve, then is a disk, and if beta is a disk with the boundary of beta equal to gamma, gamma twiddle, then the Hausdorff dimension of the image of beta is greater than or equal to 3. And the proof is roughly, and the proof ends up being essentially the same argument that we used to show that the Dane function, that the filling area of gamma twiddle was cubic. What we're going to do is we're going to say, suppose in order to bound the Hausdorff dimension, we want to say something about coverings of this disk. We want to say something about coverings of this disk by balls. So let's suppose that the image of this disk is contained in the union of a collection of balls. Say these are balls of radius r sub I and center c sub I. If the image of beta is contained in the union of these balls, then the projection of the image, the projection of the image of beta is going to be contained, and here we're projecting to the yz plane again. The projection to the yz plane of the image of beta is going to be contained in the union of the projection to the yz plane of these balls of radius r sub I around c sub I. And in particular, if beta is a disk that fills this curve gamma, then the projection of beta is a disk that fills that L by L squared triangle. And so in particular, this projection has to contain the interior of the triangle. So far we've just made nearly the same argument that we made for the filling area. We have this curve gamma twiddle, and we take the projection to the yz plane, and we look at the projection, and then we're going to try to bound the size of this disk by looking at that projection to the yz plane. Then what can we say? So how do we bound the disk, or how do we bound the radiuses of these balls? Well, we want to look at the projection to the yz plane of a ball of radius r sub I around c sub I. Well, if c sub I is the identity, if we take a ball around the identity, we just said that that a ball around the identity is roughly a box with dimensions r by r squared. So if we take a small ball around the identity, it's roughly a box like that. And so its projection to the YZ plane is going to be roughly like that. If we take a ball, and that's going to actually apply to any box with x coordinate 0, because when the x coordinate is 0, then the plane V1, the horizontal plane, is parallel to the YZ plane. And so if we move a small distance away from a point with x coordinate 0, the z coordinate isn't going to change very much. The x coordinate and the y coordinate are going to stay between minus r and plus r, and so you just don't have enough space to move the z coordinate very much. If I start with a point with larger x coordinates, say I start with a point over here, then the horizontal plane starts to tilt. Then the horizontal plane starts to tilt like that. If this point is, say, x comma y comma z, then the projection of this point to the yz plane is going to be the point y comma z, and then the horizontal plane through this point is going to project to a plane with slope on the order with slope x. And if I take a ball around this point, if I take a small ball around this point, you can check that the x and y coordinates aren't going to change very much. They're going to stay between minus r and plus r. The z coordinate is going to change, but the ball itself is going to stay in a small neighborhood of this plane. So if I take a ball of radius r around this point, it's going to be roughly the shape of a slanted parallelepiped. So this front face and this back face are rectangles, and these faces on the side are parallelograms, where the slope of the parallelogram is x. So we're going to have an image that looks something like this, where this height is order r sub I squared, and this width is order r. And so no matter where we center this, no matter where the center of this ball is, the projection to the YZ plane is going to be small. The projection to the YZ plane, the area of the projection to the YZ plane of the ball of radius r sub I around c sub I is going to be on the order of r sub I cubed. So going back to this tells us that, well, the interior of the triangle, the triangle in the YZ plane is contained in the union of the projection of these balls. And so that means the area of the triangle is on the order of L cubed, is at most the sum of the areas of these balls, or the areas of the projections of these balls. And this is on the order of the sum of r sub I cubed. And so in particular, that means that the sum over I of r sub I cubed has to be bigger than 0. In fact, it has to be bigger than the area of the, it has to be bigger than some constant times the area of the triangle. And so that means that the Hausdorff dimension of the image of the disk has to be at least 3. So this is our correspondence between the surfaces in the Heisenberg group with the Riemannian metric and surfaces with the sub-Riemannian metric. In the Riemannian metric, all the surfaces filling this curve have area on the order of length cubed. In the sub-Riemannian metric, all of the surfaces filling this curve have Hausdorff dimension 3. And in fact, you can prove a stronger statement. In fact, it's true that if beta is a map from D2 to the Heisenberg group is injective, then the Hausdorff dimension of the image of beta is at least 3. So not just surfaces filling this particular curve, but really every surface in the Heisenberg group has Hausdorff dimension at least 3. Is this okay so far? Okay, so this is so this is what happens in the three-dimensional Heisenberg group. And there's an interesting phenomenon. Previously, we saw that the Dane function of the Dane function of Sol 3 was exponential, but then the Dane function of Sol 5 was quadratic. We have something very similar here. Just like the solvable group Sol 3 had a higher dimensional counterpart, the Heisenberg group also has higher dimensional versions. We can define a group H2k plus 1, the 2k plus 1 dimensional Heisenberg group, to be the group of upper triangular, not all upper triangular matrices, but they're going to be upper triangular matrices with ones along the diagonal. These are going to be k plus 2 by k plus 2, k plus 2 by k plus 2 matrices. And I'm going to have coefficients x1 up to xk, and then z in the top row. I'm going to have coefficients y1 up to yk in the rightmost column, and then I'm going to have zeros everywhere else, everywhere off the diagonal. And then we require that x sub I and y sub I and z are all real numbers. And this is the 2k plus 1 dimensional Heisenberg group. It's a generalization of the three-dimensional Heisenberg group. And just like we saw in Sol 3 and Sol 5, sometimes adding more stuff to your group reduces the Dane function. I mean, sometimes adding more space to your group gives you more surfaces to work with, so that you can so that the Dane function decreases. And that's exactly what happens here. Here, the Dane function of h5, and more generally, the Dane function of h2k plus 1, when k is bigger than or equal to 2, is quadratic. And very roughly speaking, the reason that there's a change here is very similar to the reason there was a change in Sol 3 and Sol 5. The change between Sol 3 and Sol 5 was that Sol 5 had these flats, had these nice two-dimensional pieces. The same thing happens between H3 and H5. In H3, we have no horizontal surfaces. Every surface has Hausdorff dimension at least 3, and basically because we can't construct a surface that's always tangent to these to this distribution of tangent planes V1. Maybe I should illustrate that. So. Why can't we construct a horizontal surface in H3? Well, the natural way to try to construct a horizontal surface would be to take some region in the plane and then try to lift that just like we lifted curves in the plane to horizontal curves. But what happens if we try to do that? Well, if there's a way to lift this to the plane, if there's a way to lift this to H3, let me draw this. So here's my xy plane. If I have a surface in the xy plane, and I want to lift that to some surface in the Heisenberg group, the problem you run into is that if I draw a small closed curve here, then that would have to lift. If this were a horizontal surface that lies over this, then that small closed curve here would have to lift to a closed curve there. and it would have to lift to a horizontal closed curve there. But this curve here has non-zero signed area, has positive signed area. And so any lift of this to a horizontal curve in the Heisenberg group isn't going to close up. So there's no way to lift this surface in the xy plane to a horizontal surface in the Heisenberg group, because there's no way to lift small closed curves in this surface to horizontal curves that close up. Does this make sense? Is this okay? Okay, but so roughly the reason why is that H5 has horizontal disks, has horizontal surfaces. But H3 does not. Shoot, I skipped a whole section of, I skipped a whole paragraph in my notes. So let me, before I can clarify this, I need a little more, I need a little more setup, I think. So what do we mean by this? Because when we defined horizontal disks in H3, we only defined them for H3. How do we generalize this notion? How do we generalize this CC metric to arbitrary or more general nilpotent groups? And what does the asymptotic cone of H5, for instance, look like? So I'm going to define, so before I said that a nilpotent group is a group whose lower central series terminates. We can say the same thing for Lie algebras, for Lie groups. If G is a Lie group, then the lower central series of the Lie algebra of G terminates as well. And we define the lower central series of a Lie algebra in the same way that we defined the lower central series of a group. We define G sub 1 is equal to G. We define G sub I is equal to the bracket of G and Gi minus 1. This is exactly the same thing we wrote for the groups, for a group, except the difference is that here these brackets represent the Lie bracket, the bracket operation in the Lie algebra, before they represented the commutator subgroup. So we define G1 equals G, Gi is the bracket of G with Gi minus 1. And then we say that this terminates if Gk is equal to 0 for some k, then the corresponding Lie group G is nilpotent. If the Lie algebra satisfies a stronger condition, so normally we have, normally the lower central series is a, the lower central series is a filtration of the Lie algebra. G1 is contained in G2, is contained in G3, is contained in so on and so forth. If we can say something stronger, if we can actually construct a grading of the Lie algebra. If we can write G equals V1 plus V2 plus so on and so forth, such that we want G sub I to be V sub I plus dot 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 plus V sub K, where K is the last term in the lower central series, and we want that the bracket of Vi and Vj is contained in, I guess, do I want contained in or do I want equal? I think I want equal. Is equal to Vk, Vi plus j. In this case, if we can break down the Lie algebra of G into a product like this, where the bracket has this nice consistent operation on the terms in the product, we say that G is a Carnot group. In particular, every two-step nilpotent group is Carnot. So the significance of these groups, the significance of a group being Carnot, is that if a group is Carnot, then it has scaling automorphisms. It has a family of scaling automorphisms that's essentially the same as the family of scaling automorphisms we saw for the Heisenberg group. If G is Carnot, then the map S sub t that takes V1 plus V2 plus dot 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 plus Vk to TV1 plus T squared V2 plus dot 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 plus T to the K Vk is an automorphism. And furthermore, this automorphism is almost a scaling in the same way that the scaling automorphism of the Heisenberg group was almost a scaling. If you put a left invariant metric on your group so that all of these V sub i's are orthogonal to one another, and then you apply this scaling automorphism to the group, then this scaling automorphism preserves each of the V sub i's and it distorts each of the V sub i's according to I. It distorts V1 by a factor of t, V2 by a factor of t squared, so on and so forth. And so if a group is Carnot, then it has a scaling automorphism, just like the one that we saw for the Heisenberg group. And in particular, if a group is Carnot, then the limit as I goes to infinity of G with this left invariant metric divided by I converges in the Gromov-Hausdorff metric. And this converges in the Gromov-Hausdorff metric to G equipped with the Carnot, with the CC metric, where instead of the horizontal vectors that we used for H3, the horizontal vector space is V1. Okay? So if we have a Carnot group, in particular, if we have any two-step nilpotent group, then we can do exactly the same construction as we did with the Heisenberg group to get its asymptotic cone. More generally, if we have groups that are nilpotent but are not Carnot groups, we can't use exactly the same construction, but we can use nearly the same construction. And the asymptotic cone of a group that it turns out that the asymptotic cone of a nilpotent group that's not Carnot still has a CC metric. It's just a little bit more complicated to describe. Is this okay so far? Okay. So in particular, So we can apply this to H5. So remember, H5 is a group of 4x4 matrices, x1, x2, z above the diagonal on the top row, y1 and y2 in the rightmost column. And it has Lie algebra. I guess I've been writing these as superscripts. It has Lie algebra generated by 5 vectors, which I'm going to call x1, x2, y1, and y2, and z. And we can break this down into a grading, where the first level of the grading is x1, x2, y1, y2. And the second level is generated by z. And then because we can break it down as a graded Lie algebra like this, in order to describe the bracket on this Lie algebra, we just need to know if I take 2 vectors that are in V1 and I take their bracket, what do I get in V2? I need a bilinear form from R4 to R, because all the other brackets I know. I know z bracket itself is 0. I know that z bracket anything in V1 has to be 0, because anything in V1 bracket anything in V2 would have to wind up in V3, but there's no V3. So all I need is I need to know the bracket on V1, and the bracket on V1 is that xi bracket yi is equal to z, and that xi bracket yj is equal to 0 if I is not equal to j. And this calculation, you don't have to take my word for it. You have an explicit representation of the group as a set of matrices, and so you can do the appropriate calculations with these matrices. You can calculate commutators of xi and yi and xi and yj to show that in fact this is the right bracket. So this is graded, and so this means that H5 is Carnot, and so we can equip it with a CC metric where the space of horizontal vectors is exactly this. And furthermore, what happens in H5 that didn't happen in H3 is that I have pairs of horizontal vectors that commute. I have, for instance, if I take xi, x1, and y2, those commute. If I take x2 and y1, then those commute. If I take certain combinations, if I take x1 plus x2 bracket y1 minus y2, then these commute, all of these commute. And so all of these commute. In fact, I have a whole one-dimensional family of pairs of vectors that commute like this. And each of these pairs of vectors that commute is going to give rise to an abelian subalgebra of the Lie algebra. It's going to give rise to an R2 inside H5. And furthermore, because these R2s are generated by horizontal vectors, that means that these R2s are tangent to the these R2s are tangent to the horizontal planes. So these are not just don't just correspond to an R2. These actually correspond to a horizontal R2. And so we have in H5 a bunch of horizontal surfaces that we didn't have in H3, and it turns out it turns out, and this is proved by several different people, but I think the first was Gromov, that any horizontal curve in H5 bounds a disk, a horizontal disk. and I should say something stronger. If it bounds a horizontal disk of area at most, and so let's say this curve is of length at most L, then it's going to bound a horizontal disk of area at most on the order of L. Is this okay so far? Okay. And the idea behind this is really a scaling argument. This is really a scaling argument. It turns out to be enough, and I really shouldn't say I'm going to prove this because I'm not. It's enough to show that every curve of length at most 1 bounds a horizontal disk of area at most C, at most some constant. And really, I think you can use a compactness argument here. So really, it's really enough to show that every curve of length at most 1 bounds some horizontal disk. Because if you can show that every curve of length at most 1, every horizontal curve of length at most 1 bounds a horizontal disk, then you can use the scaling automorphism to fill arbitrary curves. Then if gamma is a closed curve, is a horizontal curve of length L, we can use the scaling automorphism to shrink this down to a curve of length 1. And if you can show that every curve of length 1 bounds some horizontal disk, then that means that there exists some beta some horizontal beta and such that the boundary of beta is equal to this scaled down version of gamma, which means that the boundary of the scaled up version of beta is equal to gamma, and then the area of the scaled up version of beta. The significance of horizontal curves here, the reason that why we're interested in the significance of horizontal disks here, the reason that it's important that these disks are horizontal is because horizontal disks are exactly the disks that scale linearly, or I guess since they're two-dimensional, they scale quadratically. So this is L squared times the area of beta. And this is not going to be true of every disk. I mean, if you take the disks that we saw before in H3, the disks of Hausdorff dimension 3, if you scale those by a factor of L, because they have Hausdorff dimension 3, their area is going to grow by a factor of L cubed. But because if we have a horizontal disk, if beta is horizontal, then that means that all its tangent vectors, it's always tangent to these horizontal vector spaces, these horizontal tangent planes, and the scaling automorphism scales each of the horizontal tangent planes by a factor of t. And so if we scale beta up by a factor of L, its area scales by L squared. And so in particular, the area of this scaling is going to be at most CL squared. So really, it turns out to be enough. Gromov proves this by showing that every horizontal curve of length at most 1 bounds a horizontal disk of area at most C. And he does that by basically showing that a certain partial differential equation is solvable. He does that by writing the condition of being horizontal as a PDE, and then showing that this PDE is something called infinitesimally invertible, which is a concept due to Nash. And if you have a PDE that's infinitesimally invertible in this way, then you can solve it for any choice of boundary conditions. Is this okay so far? So why? So why? So why did I want to show you this? Why did I want to talk about nilpotent groups and Dane functions of nilpotent groups? So really, the idea. The idea behind a lot of this is that the exponent that shows up in the Dane function of a nilpotent group should have a lot to do with the geometry of surfaces in the asymptotic cone of that nilpotent group. And that's what we saw here. In H3, the Dane function is cubic, and that corresponds to the fact that, every surface in H3, every surface in the asymptotic cone of H3 has Hausdorff dimension 3. The Dane function of H5 is quadratic. That corresponds to the fact that every horizontal curve in H5 can bounds a horizontal disk of quadratic. Sorry, that corresponds to the fact that every horizontal curve in H5 bounds a horizontal disk, that is a disk of Hausdorff dimension 2. And in some cases, in some cases, this connection is known rigorously, or at least we can get something very close to this connection rigorously. So there's a theorem of Stefan Wenger that says that if G is a Carnot group and the Dane function of G is on the order of L squared, then every closed curve every horizontal closed curve in G omega in the asymptotic cone of G bounds not quite a horizontal disk, but bounds what's called an integral current. Of area, and let's say the curve is of length L, an integral current of area at most on the order of L squared, and an integral current is nearly a horizontal disk. On the other hand, this same argument of Gromov that says that if every horizontal curve bounds some horizontal disk, then by compactness, every horizontal curve of length at most 1 bounds a horizontal disk of area at most c, and then by a scaling argument, every horizontal curve of length L bounds a horizontal disk of area at most c times L squared. On the other hand, if G omega has enough horizontal disks, then the Dane function of G is going to be quadratic. So at least in the case that the Dane function is quadratic, there's a reasonably close connection between the Dane function being quadratic and there being a lot of horizontal disks in the asymptotic cone. The real question, the open question, is what happens when what happens for higher what happens for when the Dane function of the group is strictly bigger than quadratic. The sort of thing we could hope for is maybe being able to say that if the Dane function is cubic, then every If the Dane function is cubic, then maybe every horizontal curve bounds some disk of Hausdorff dimension 3. If it's quartic, then they all bound a disk of Hausdorff dimension 4, and so on. But I mean, like I said before, with that, like we saw before with asymptotic cones, when the Dane function is bigger than quadratic, a lot of things don't transfer very well. A lot of surfaces don't transfer very well, and so not very much is known about what happens in nilpotent groups when this Dane function is bigger than quadratic. One would expect something reasonably nice to happen. One would expect that even in the Heisenberg group, where even in H3, where the Dane function is cubic, one would expect, or at least hope, that if you took a curve of length L and you filled it by a minimal disk in the left invariant Riemannian metric, and then you took the limit as L goes to infinity, you would hope at least that that wouldn't behave too badly in the limit. I mean, you would hope at least that that minimal disk would converge nicely in the limit, but not much is known. Not much is known. Well, maybe things are known in the Heisenberg group, but not much is known in the general case. So is this okay so far? Are there any questions about anything so far? Yeah, any Carnot group. The asymptotic cone is just that same Carnot group except with the CC metric. So let me, I guess I have about 15 minutes left. So let me tell you, I haven't really prepared this very much, but let me tell you about one of my favorite theorems in this direction. In the examples we saw so far, H3 and H5, the Dane function was quadratic or it was cubic. For a long time, there was a conjecture about whether or not the Dane function of a nilpotent group is always a polynomial, always has exactly the same growth rate as a polynomial, whether you can ever have fractional exponents or n squared log L or L squared log L or anything like that. And a couple of years ago, Stefan Wenger proved that there is a nilpotent group G with the Dane function of G. He didn't compute it exactly, but he showed that the Dane function of G is at most L squared log L, and at least, actually strictly bigger than L squared. So in particular, the Dane function is not asymptotic to a polynomial. Right. So we don't know. It's still open exactly how quickly the Dane function grows. I think the conjecture is that it probably grows on the order of L squared log L, just because we can't think of any good reason why not. But from what we've discussed, from what we've been discussing, if the Dane function is really L squared log L, then the horizontal disks that fill horizontal curves ought to be interesting. The disks filling curves in the asymptotic cone ought to be interesting, ought to have some weird geometry. And that turns out to be exactly what happens. So the way he proved this, the lower bound follows from the theorem. Is it still on the board now? The lower bound follows from this theorem about integral currents. He constructs what he does is he constructs a nilpotent group where which has a lot of horizontal disks. What he does is he starts with a nilpotent group with Dane function on the order of quadratic. And because the Dane function is on the order of quadratic, we know by this theorem from before that it has to have a lot of horizontal disks, or at least it has to have a lot of integral currents. In fact, it has a lot of horizontal disks, and you can construct pretty much, you can construct the filling of a horizontal curve by a horizontal disk pretty easily. So you start with some h with quadratic Dane function and a lot of horizontal disks. Then h, the Lie algebra of h, this is going to be a Carnot group, so this is going to be, we can write the Lie algebra as a gradation v1 plus v2. And then what we do is we take some z in v2 and we consider g that we get by quotienting out by z. And if we're careful, so what happens to our nilpotent group when we quotient out by z? Well, the topological dimension goes down by 1. But because we're only affecting v2 and we're not touching v1, the dimension of the space of horizontal vectors stays the same. And if you're careful, you can arrange so that when you quotient out by z, you don't change what horizontal disks exist. If you're careful, then you can quotient out by z in such a way that every horizontal disk in the quotient is the quotient of a horizontal disk in H. So horizontal disks in G are all quotients of horizontal disks in H. But if horizontal disks in G are quotients of horizontal disks in H, then you just barely don't have enough horizontal disks to fill an arbitrary horizontal curve. Why is that? Well, if I have a horizontal curve in G, it also lifts to a horizontal curve in H. But just like we saw with the projection of the Heisenberg group to R2, you can have horizontal curves, you can have closed curves that lift to curves that aren't closed anymore. I mean, you don't have a guarantee that a closed curve will lift to a closed curve. And the reason why is that that G is a quotient of H. And so if I have a curve in G, so for instance, if I have a curve in H, if I have a horizontal curve in H between 0 and Z, that's going to be a curve that's not closed, a horizontal curve. And when I project it to G, it's going to become a closed curve. So there are going to be curves in G that don't lift to horizontal curves in H. So okay, so let's let gamma be a horizontal curve in H from 0 to Z. Then the quotient, let's call it Q of gamma, is a closed curve that can't be filled by a horizontal disk. And how do we know that it can't be filled by a horizontal disk? Well, it can't be filled by a horizontal disk because if there were a closed curve that filled the quotient of gamma, then that horizontal disk would lift to a horizontal disk in H. And because of the way we constructed H, because we know about, so if we had a curve that filled Q composed gamma, or sorry, if we had a horizontal disk that fills Q composed gamma, then it lifts to a horizontal disk in H, and the boundary of that horizontal disk would be a closed curve that doesn't lift to a closed curve in H. So if this were filled by a horizontal disk, then that would mean that we can lift the boundary of this to a horizontal closed curve. And we can't lift this to a closed curve, so there's no horizontal disk that has this boundary. Does that make sense? So yeah, if we can lift any horizontal disk to H, that means that we can take any closed curve that's part of a horizontal disk and lift that to a closed curve in H. This is a closed curve that doesn't lift to a closed curve in H, so it can't be part of a horizontal disk. And so there's going to be some curve in G that's not the boundary of a horizontal disk. And so in particular, that means that the Dane function of G has to be strictly bigger than quadratic, because nilpotent groups with quadratic Dane functions have asymptotic cones where every horizontal curve can be filled by a horizontal disk. So on the one hand, we have this group which has this one horizontal curve, or just a few horizontal curves that can't be filled by horizontal disks. But on the other hand, because H started with a lot of horizontal disks, G still has a lot of horizontal disks. So this gives us our lower bound, because we find some closed curve that can't be filled by a horizontal disk. But we can also get an upper bound because gamma can't be filled by a horizontal disk, but it can nearly be filled by a horizontal disk. It can be filled by something that's extremely singular, namely. So let's say that this is my curve gamma, right? Say this, or sorry, actually, I need this to be, this is my curve Q composed gamma. This is my curve Q composed gamma. This is a curve in G, and it cannot be filled by a horizontal disk because it doesn't lift to a closed curve in H. But any curve that does lift to a closed curve in H, we can fill it by a horizontal disk by taking the closed curve, lifting it to H, filling it by a disk in H, and then projecting back down to G. So I can't fill this by a horizontal disk, but I can scale Q composed gamma down by a factor of 2 and go around it 4 times. Four times around the scaled version, and then once around Q composed gamma. That's a closed curve. It lifts to a closed curve in H. What does it represent? What group element does it represent? Well, the lift of Q composed gamma is gamma, so that takes you from 0 to Z. And then the lift of the 1/2 scaling of Q composed gamma lifts to the 1/2 scaling of gamma. The 1/2 scaling of gamma connects 0 to 1/4 Z. So if I go around Q composed gamma once and then go around half of that 4 times, then that's going to lift to a closed curve that goes up to Z and then down to 3/4 Z, 1/2 Z, 1/4 Z, back to 0. So this can be filled by a horizontal disk. Okay, that gets me part of the way. Then I do the same thing. Except now I go around 1/4 Q composed gamma 16 times. Right? I have to go more and more times because I'm scaling by a factor of 4 when I scale down by a factor of 2. So I go around this 16 times, and again, between here and here is a closed curve. So I fill it with a horizontal disk, and so on and so forth, all the way down until I get, well, I can keep on doing this indefinitely. The problem is that when I do this, if I start with Q composed gamma, and then I connect that up to 4 times 1/2 Q composed gamma, and then I connect that up to 16 times S1/4 Q composed gamma, what do I have? Well, I said I can fill this by a disk and say this has area A, and A is going to be on the order of L squared because, well, that's the Dane, because what we're really doing is we're taking this curve, we're filling it in H, and H had quadratic Dane function. So here we have a filling of area A. We can do the same thing. 1/2 Q composed gamma forms a closed curve with 4 copies of 1/4 Q composed gamma. So I take this disk and I scale it down by a factor of 2. And each of these is going to get filled by a disk of area A over 4. And then I do the same thing to go from 16 to 6 to, from 1/4 to 1/8, from 16 copies to 64 copies, and each of these gets filled with something of area A over 16, and so on and so forth. And can you see the problem here? What happens to my area? This strip we have area A. This next strip, also area A. This next strip, also area A. Normally, you hope that when you do smaller and smaller things, you hope to be able to get smaller and smaller areas, but that's exactly what fails here. We can do infinitely many strips like this, each of the same area, each connecting a larger and larger multiple of smaller and smaller scalings of Q composed gamma. And so what happens in practice? So what that means is that we can fill Q composed gamma with something that's not quite a horizontal disk, because you can never make this piecewise smooth. But I can fill it by if I go on forever, I can fill it by something that's like a horizontal disk, but that has infinite area. Or if I'm working in the Riemannian metric, eventually after log L many iterations of this, I stop. After log L many iterations, I have many copies of the 1/L scaling of Q composed gamma. That's just a curve of length 1, say. And since we're in a Riemannian metric, I can just fill that with just a Riemannian disk of area, constant area. So in the sub-Riemannian metric, I have to go on forever. I can never stop. I end up with a filling of infinite area. In the Riemannian metric, I can stop once I get curves that are small enough. I end up stopping after log base 2 of L steps. And so I end up with a disk of area on the order of L squared log L. And so that's where the upper bound comes in, that the Dane function is less than or equal to L squared log L. And and we already showed that the Dane function has to be strictly greater than quadratic. And so this is an example. If you can construct a group that does this, and it's not too hard to construct a group that does this, then this is an example of a group that's nilpotent, but has a Dane function that's somewhere between L squared and L squared log L without being equal to log L, or without being equal to L squared. Okay, thanks.